Let's talk about torque or rotational force.
Rotational force, usually called torque, is a little bit different than ordinary force. Here we've got two children on a teeter-totter, and they're in balance. The teeter-totter isn't moving. But you'll notice the weights of the children are not in balance. The boy is heavier than the girl. And that gets made up for because the girl is farther away from the rotational axis here at the fulcrum. And the boy is closer to that rotational axis. So these rotational forces, these torques, they're not just going to depend on the force. They're also going to depend on these distances here. And this distance from the rotational axis to where the force is applied, that's usually called the lever arm. And typically, we're going to give it a symbol R or sometimes L.
You've probably marveled at the brilliance of engineers because they always place the doorknob as far away from the hinges as possible. So here's your axis of rotation at the hinge. Here's where the doorknob is. That means you're maximizing your lever arm distance. If you've ever tried to push a door open close to the hinge, you'll find that it rotates open very, very slowly. It's very hard to rotate the door open if there isn't much lever arm distance. What's more, what those engineers do is they always place the doorknob perpendicular to the surface of the door, so that the force that you're going to apply is always going to be perpendicular to the door surface. If you apply a force in this direction, you won't get any torque at all. So this torque, it depends on the force, the lever arm distance, and also the angle at which you push the door open. And this leads to a general formula for torque. So we usually use a capital letter tau, a Greek letter tau, for torque. And it's going to equal R, which is simply the lever arm distance, times the force, but we don't get to keep all the force. Only the component of the force that's perpendicular to the door surface is going to produce torque. So, for example, let's say that we produce a force like so, and there's an angle theta here between the door's surface and the force. Then we'd only get to keep this component here, that component F perpendicular. And since F perpendicular is opposite the angle, F perpendicular is going to be equal to the force times the sine of that angle theta. So our formula for torque is going to be R times F times the sine of theta. F is the force, and theta is the angle between the lever arm and the force. So here's a bit of practical advice. Last summer I wanted to save a little bit of money, and I changed the oxygen sensor on my car. Well, the oxygen sensor is located below the engine, so it's really, really hot where the oxygen sensor is. And that means the bolts tend to fuse. So an oxygen sensor pretty much always fuses to the casing of the engine of the car. So I did have to buy a special socket for the oxygen sensor. But what I also did is I went to Canadian Tire and bought myself a piece of steel pipe. And I fit the steel pipe over top of my wrench. And of course, that extra length gave me a lot more torque. So I did get the oxygen sensor off my car without breaking it. Now when I put the new oxygen sensor on, it didn't fix the problem. So because I didn't break my old oxygen sensor, I just simply put it back on the car, and I took the new oxygen sensor back to the store for a refund.
Let's try a couple of examples. Pause the video, read the question over, come back for the answer. So in this question here, the first thing you want to realize is that in this particular position here, there's going to be no torque. And that's because the force is going right through the axis of rotation. So that force can't exert any torque. The maximum torque is going to be exerted when the person puts all their weight on this foot here. And it's a 60 kilogram person, so their weight is approximately 600 newtons. And since all their weight is on that right foot, there won't be any weight on the left foot, and that pedal can come up freely. Now to calculate how big that torque is going to be, we know the lever arm distance from here to here is 0.18 meters. So to calculate our maximum torque, take the lever arm distance, multiply it by that force times the sine of 90 degrees, which is simply 1. So it'll be 0.18 meters times 600 newtons, giving you approximately 110 newton meters. Be careful about the unit, the newton meter. When we were studying energy, a newton meter was the same as a joule. But energy is a scalar. Torque is actually a vector. So when we're talking about torques, a newton meter is not the same thing as a joule. Keep that in mind. And finally, what might the bicyclist do in order to exert more torque? Well, one thing they could do is increase the lever arm distance here and have longer pedals. You might also talk about the gears and changing the radius of those gears to exert different amounts of torques. You might also talk about a person could grip the frame of the bicycle and push down with their muscles and thereby exert a bigger force than their own weight.
Here's a final example taken from Surway and Vaughan's College Physics. What I'd like you to do is read it over, try it out for yourself, come back for the answer. Okay, so torque is equal to lever arm distance times force times the sine of the distance between the lever arm and the force. So our lever arm distance here, that's the 2.00 meters. The force is 100 newtons. And the angle between the lever arm and the force is 57 degrees. Multiply that out and you should get a torque of 168 newton meters. And that's all for today, folks. Thank you very much.